Today we're going to start with the simulation piece. We did that last time at the very end of the low resolution spreadsheet where we did just, the box was divided into 10 increments and we only had 2 quantum states and we could only model 1 transition between 2 levels. Today we're going to have the 15 quantum states and we're going to be able to model 225 transitions. Half of those are 0, so we're down to 100. And then most of those are really low intensity, like all of the plus or minus 5, 7s, and 9s. We're not going to model those because they're just so small they don't really figure in. So we're really going to model 36 peaks for the particle in a box, and I think that's what's in your handout. So make 36 columns and do the 14 delta n plus 1, and then do however many plus 3s and so many plus 5s, and then that's all you'll have. So you're only going to model 36 peaks. But once you've modeled 36 peaks, you could do 100, you could do 5, you can do any range then. So we're going to talk about how to build a spectral simulation worksheet today. Now this is focused on the particle in a box, which is of limited applicability. I agree with that. But once you learn how to model the spectrum with that, then you can just throw away all of the particle in a box stuff and the wave function stuff and take the output from Gaussian and put it into the same spreadsheet. And then you can model spectra straight out of Gaussian. So this is the simulation process that we're going to go through today. We have the Schrodinger equation with the wave function, the transition moment integrals, all of this done in Excel. Then we do the Boltzmann piece, and then we add a line shape. And so there's going to be a good chunk of information about the line shapes today. So we'll just review some of this. So the Schrodinger equation, look how smooth they are. In the low definition spreadsheet, they're real choppy because we had 10 increments. Now we have 100 increments between the left and right side of the box. And you can see that they're really, really smooth. These are the first 4 quantum states. You can see this one here, this is the ground state. The least curved one, doesn't even go through 0. It starts at 0 and ends at 0, but has no nodes. That's the n equals 1. And then n equals 2 is the next one, the red one. It has 1 node. N equals 3 has 2 nodes, the green here. And n equals 4 has 3 nodes. And they go up in energy accordingly. Now we could have plotted the n equals 15 and so on, but it would just be, quite a bit. Now you're going to build this. So you're going to put in the wave function formula and so on and anchor the cells and do all of that. And you're going to plot these. And if you want to see that n equals 15, then you can just scoot this thing over and plot that one and play around with it. It's your spreadsheet and be curious. That's one thing I'd really, I like about grad students typically, is that you're more curious. Okay, the undergrads I typically classify as just scared. Right? This is on tape, but anyway, they just want to get the right answer, But I want y'all to be more curious. You're building this thing, play around with it. Once you get it working, like you're saying, you're having trouble with some of the cells and so on, but once you get it working, then play around with it. Change the temperature, change the mass, change Planck's constant. What if we're in a different universe? What if the multiverse is real and now we have a universe with Planck's constant and it's not 10 to the minus 34, it's 10 to the minus 35. What would that do to the spectrum? You can play with all of that stuff. Okay, so here's our wave functions, and we can check to see if they're normalized by multiplying them by each other. So we're going to take every wave function and multiply it by every other wave function. We're going to do that numerically, and we're going to use matrix multiplication to do that. And we're also going to take the derivative. Oh, this is the Schrodinger equation. I'm sorry. So we're going to take the derivatives. So looking at this in the Schrodinger equation, we want to solve for the energies. We take the second derivative of the wave function, and then we left multiply by that wave function, and then we integrate over all space. Okay. So this numerically, we need to talk about these derivatives, because how do we do it? We know that it's rise over run. That's how we described it when I was a little kid, when you're talking about the slope of a function. So what do we mean by rise? Well, you take the change in y, that's how much it goes up or how much it goes down, that's what we call the rise, and divide by the change in x. Okay, that's fair enough. Anybody can do that. But now you have a result. You have y divided by x. Where do you put that point? That's the question. If we put that point where we're standing, if we're taking x at point 0 and we look forward, we take the y and the x in front of us and we plot it where we're standing, you know, in that point, then we've pulled the curve this way. So we've shifted the curve by taking the derivative. If we look forward, we're shifting it back because we're plotting the point where we are right now. So I, you know, x at I and x at I plus 1, okay? If we do y1 minus y and x1 minus x, then we're shifting it back by plotting it at x. Well, the opposite, if we did y evaluated at the previous x point, so y minus 1 minus y and x minus 1 minus x, then we would be doing reverse or backwards differentials, and we would be shifting the curve forward. So the only way not to shift the curve either way is to go forward and back. So take y plus 1 minus the y at the previous point, y minus 1, and then divide that by x plus 1 and x minus 1, the difference in there, and then plotting it at x. So that's the center derivatives. And you can see this here. The forward slope is down. See this difference in y? It's negative. If we plot that here, we're saying the slope of this curve at this point is negative, and it's not negative. Or if we did the previous point and compared it to this point, the slope would be positive. And if we plotted it right here, then it would say the slope of the curve at that point is positive, and it's not positive. What is the slope exactly at that point? It's 0. Okay? So we want to do a symmetric derivative. We want to do the next point minus the previous point, both in y and x, and we take the difference, and then we'll get a slope of 0, and we'll plot it at that spot. So we'll get the true tangent right there at that curve, and it would be symmetrically preserved. That's why we're taking centered derivatives. So I've got a picture of this. So that's the forward slope, and we get an incorrect slope if we plot it at that middle point. This is the reverse or backward slope, and we get an incorrect slope if we plot it there. But if we do this centered derivative, it's beautiful. We get a 0 slope right there where it should be plotted on that point. So that's why we have to have this extra couple of rows of data. Because when we take these differences and then plot them at that point, we lose a row of points. Okay. Now that also applies down here, it's, this forward slope, backward slope, or centered slope. So this is also going to be, a positive slope. If we do the centered derivatives, we get a correct one. If we do the centered derivatives here, we get a negative slope. So it preserves all of the slopes. Okay. And they go, they go correct at the ends too. So that's how we would do that. We would do centered slopes twice and get our centered derivatives. Okay. So if we take that first derivative, this is what we get. So here's our psi functions. So now we have psi prime. You see up here at the top, psi prime. So we've taken the first derivative, and this is what we're plotting. And remember that n equals 1, it had a 0 slope, and now it's 0. But if we go to the right and the left, you see the slope is decreasing. And so this is the first derivatives of those functions. Okay. Also, we see how they behaved over here at the far left. These were all sine functions, and so when we take the derivative of sine is cosine, and you see cosine, starts at its maximum value in all of these situations. So we see that. Now we take the derivative of the derivative. So and also look up here. We lost a row of data after taking that first derivative. So then the second derivative, we're going to lose another row. So here's psi double prime, right? Which is that second derivative of psi. These started out as sine functions, right? They went like this, and then now we did the derivative of that gave us cosine, and then the derivative of cosine gave us minus sine. So notice that they go negative first instead of positive. So we should see that. Yeah, they flipped. So we started out with sine and we went to cosine, now we're at minus sine. And we didn't have to know any of that because we're doing it numerically. But we do know it from calculus. But even if we didn't know it, just taking the differences in y and dividing by the differences in x, we get all of those trigonometric things that we know right here in the spreadsheet. So that's really satisfying, I think. Okay. Now some constants have been coming out front when we do these, and the more curvy the function, the bigger the constants. And so look at this, the least curvy function, this one right here, and this is kind of some of your discussion questions that I'm talking about now, that the energy is related to the curvature of the function. Okay, and notice when we pull those arguments out of inside of that function, they become coefficients and they multiply by the curve. And notice that the most curvy curve here, psi 4, is the tallest amplitude. And the least curvy curve is n equals 1, and it's the smallest amplitude. So we can actually see the energies coming out. We take the second derivative, and now the amplitude differences are the energies. If we could take those energies out, we would see that they were the energies. So that's what they have. And so that's these pieces out front. Now we can do this in Excel by taking this transpose of that wave function block times the double prime block of wave functions. It's a 15 by 100 matrix times a 100 by 15 matrix. This is helpful when you learn, you're selecting these and you're going down 100 points. I mean, you can use the mouse. 100 is not too bad, but you can also put the cursor there and hit Control Shift right arrow and down, and it will go and select that whole block. So I think I talked about that in the boot camp, using Control Shift to select things and so on. So use your shortcuts and that'll just make it faster. And that ends up being a 15 by 15 matrix. So we take this block, we transpose it. Now it looks like this in Excel's brain. We don't see this, but when we transpose it, Excel flips it like this, and then we multiply it by the double prime inside that M mul. So the transpose psi gives us this here, and then the M mul takes this times that, and you have this 100 item vector here multiplied by this 100 item vector added together, and that gives you the first cell, the first integral. Times dx, don't forget to add the dx in there, right there, and that's on the control plane. And so we end up with our energies. So here's our energies that come out of this. So all those diagonal elements, those are the energies. So this is, you can look at the quantum states. So this is n equals 1, and that's the energy for n equals 1. Here's n equals 2, that's the energy, etc. So these are the energies that come out. And why are these 0? Yeah, orthogonal. These wave functions are orthogonal, and so if you have wave function 1 and wave function 4 and they're multiplied by each other, all those go to 0. And so you'll have some complicated curves, but all of the positive numbers and the negative numbers are the same magnitude, and so when you sum from left to right, it all cancels out and you end up with 0. So the diagonals of this Schrodinger equation matrix are the energies, the eigenvalues for that equation. Yes. Yes. This is, yeah, so we solved the analytical energies, right? Is that what you're saying? Why not just use that equation? Yes, that would be the way to go. Like if I was to calculate the particle in a box energies, I would use the analytical results because I know them. But when we get to molecules, we don't know those analytical solutions. So you're correct. For a particle in a box, it doesn't make really a lot of sense to go through this. What we're doing here is just doing we're doing the numerical method to compare it to the analytical method to say, okay, now I understand all the pieces. So when I go to Gaussian, Gaussian's doing the numerical pieces because it doesn't have an analytical answer. Yeah, so when we start modeling 3D molecules, we have no analytical answer. So we have to use an approximation. That's it. Yeah. And we'll see that this isn't perfect when we get to this comparison of the energies. I don't see it here, but you'll calculate that. You'll have a table of the analytical energies and the numerical energies, and you'll see they're quite good for the low quantum states. You know, an error of like 0.3%, I think, if I remember correctly. Very low error, less than 1%. Okay. For our low definition spreadsheet with only 10 increments, what was the error? It was crazy. Yeah, it was 10 times worse, right? And so when we increase the number of when we increase the fineness of our grid, that's the technical term. So we divide our grid into a finer number of divisions. We went from 10 divisions to 100 divisions, and our error dropped by an order of magnitude, which we'd expect. Yeah, it went from say 3% to 0.3%. And so that's what you see with numerical analysis. The finer your grid, the lower your error. Yeah. Okay, so then we have the transition dipole moment integrals, the intensities. So let's cover those. So this is the X psi. So we have another sheet. We'll copy that over, control drag the sheet over so we have all our quantum numbers and our X and everything like that. And then you go in and you edit the formula, and now you just take the wave function on page 1 and you multiply by the x-axis and copy it down and copy it over. And so then you end up with this. And these are the wave functions. Now remember in your mind the ground state wave function, it was just this curve like that. And now we've multiplied it by the x-axis. And so the x-axis is negative on the left, and so you see we've dropped that left side down below the axis, and now it crosses 0 and it goes positive on this because the x-axis is positive over here, so this side stays positive. We've taken this function, we're going to really get into this later, and taken this even function and made it an odd function by multiplying by an odd function. I'm just sort of putting that in your brain that there's a certain thing called an even and odd function. So we'll get to that someday, but notice it was like this, and now it's like this. It goes through 0 in the middle. That changes its nature when I then multiply that by a wave function in the upper state that also goes through 0. Now these wave functions are more compatible. So when I integrate them over all space, I get a non-zero result. You know, 1 and 2 were this off-diagonal element here, right here, let's just look at this one, was 0 because when I multiplied the wave function 1 times wave function 2 and integrated that, it was 0, right? Because again, this positive piece and this negative piece cancel each other out. But now, so this is psi 1, this is psi 2. If I take x times psi 1, it now looks like this. Oh, let's see, it looks the other way. It looks like this. And then I'm going to multiply that by psi 2 and integrate over all space. And now look how similar they look. Don't get worried about them being the opposite sign of each other because we're going to square this integral. And so this is going to end up being, not equal to 0. It's going to be some number, some negative number. We're squared, it becomes positive. But the point is, it's not 0 anymore. Why? Because light came in, and now light can cause a non-zero result between wave function 1 and wave function 2. That's a transition. We've gone from 1 to 2, or at least we're able to. So that's what we have here. These are the dipole modified wave functions. You can think about these as this is the initial state, and light comes in and it messes with the wave. You've got a wave like this, and you've got light, which is an oscillating electric dipole, and it's coming in like this, and it interferes with that wave and makes it compatible with an excited state. And because it's compatible, then you can have a transition. It can absorb that photon. So let's do those integrals. Once again, we're going to use the matrix multiplication. So when we transpose psi, we get that thing on the left. When we multiply that by x psi, we have again 100 by 15 for that. And we end up with this 15 by 15 matrix. And this is the selection rules that we get. So we have to select that whole block. We type in equals m mult, open parenthesis, transpose, open parenthesis, then we go select the psi block. We're only picking the ones inside the box. Don't get the extra rows on the top and the bottom. Ignore those. Those are just for the derivatives. So just take the box. And then comma, and then go get the x psi block, close parentheses, times, and go to the control sheet and get delta x, and then hit control, shift, enter, and you get all 225 integrals. It's so satisfying to do 225 integrals like that. And you could do 10 times more. It's so fast. Yeah. You know, they used to have all these integration techniques in the numerical cookbook. I mean, if you're old like me, you wanted to do computational chemistry, and they had like code. This is like this is so old. But it was a book that had little routines that you could put in that had machine code that could do integrals as fast as a computer could do them, because you're doing them down like at chip level. And you could type all these strange things in. It was, you know, it was like what we get out of AI, but it was all text-based. Like you had a book with machine code. It was called the Numerical Cookbook. And now we don't have to do any of that. We can get Excel to do it. You know, this was even before there was an Excel. So here we are. The integrals are 0 when delta n equals plus or minus 2, 4, and 6. And they're non-zero when delta n equals 1, 3, and 5. And the non-zero ones are what we call the selection rules. Okay. So we see those selection rules. One of the options, I think, in your assignment or your project is to do the Raman and Rayleigh scattering selection rules. Did I put that in the assignment? I think I did. Down at so it's like the part 2, yeah, down at the bottom, sort of what you get to do, like to play with it, is to go and do the Raman selection rules and Rayleigh scattering selection rules. And so instead of x psi, you have x squared times psi. Super easy, right? You just take the x-axis times the x-axis again times the wave function, x squared times psi. And then you'll get different selection rules. And I want you to tell me what they are. Yeah, so it's pretty neat. That was really thrilling. First of all, I was excited when I got this, and I thought, there's no way it can be that easy. I just change it to x squared, and I got the Rayleigh and the Raman scattering selection rules. So it's amazing. Then I did the rotational spreadsheet, and I thought, this can't be possible, that it would be this easy. Instead of light being just x there, in that case, since we're rotating, light becomes a cosine. And so it's a cosine of the rotation axis. And I put that in there. Now, the rotation selection rules aren't 1, 3, 5, and 7, and so on. They're just plus or minus 1. And I thought, I don't believe that it's going to just get plus or minus 1 and not the 3 and the 5 and the 7. And it does. So I did the rotational selection rules, and it came out. So I thought, okay, now I really feel like I understand what's going on with spectroscopy and the selection rules. And I'm just using the simple one-dimensional system. So this really is a powerful way to go about it. All right, so this is, let me review, which axis of the spectrum. So you got a spectrum. What axis is this related to? So you got the vertical axis and the horizontal axis. Which one is this related to? Intensity. So the vertical axis. Good job. So this is about the vertical axis. Now let's do the transition equation, which is the horizontal axis. So where are the peaks? This tells us if they're going to be there or not, but where are they located? That's the horizontal axis. And those are the transition equation. Be careful, there's a transition equation and there's transition dipole moment interval. Both of them had transition in there, so that's not going to be enough, okay? This is the transition equation to tell you where on the horizontal axis the transitions occur, and the transition dipole moment integral, think integral intensity, that's going to be the vertical axis. So this is just taking all n+1 transitions. It's just a bit of algebra just to show you. So if we want to know the energy differences for all delta n+1s, we can put in E of n+1 and subtract E of n. So everywhere there's an n in the energy equation, we get this. Everywhere there's, we put in n+1, and then we put in n, and then we do the algebra. We pull all the constants out front. We do FOIL here, first, inside, outside, last. That's FIOL. Okay, and then we said we can cancel the terms, and we end up with this. I pull that 2 out just because it's very nice to see the n by itself here. And so that's our transition equation for all the single jumps in energy levels. We could do the 3's. So now we have n+3 here. It's the same algebra. We pull out a 6 now, and we have this equation, and then we can plot those. Then we do the Boltzmann distribution. So in our spreadsheet, this is what it's going to look like across the peak area. Go ahead and label your peaks out to 36. You can do delta n's equals 1, and then 3, and then 5. We do a few 5s. And so then let's go ahead and just label our n's. So we have n equals 1, 2, 3, 4, 5, and so on. And then we have n prime. See here, this is the final state. Since we're doing delta n's, so that we can just say this is equal to n plus delta n. So just put a formula in there, and so then you can copy it across. Here you can go and look up those energy values from that matrix. We don't want to use the analytical equation here. Let's use the numerical equation since we're doing the numerical energies. And there's some tips in the handout about how to use VLOOKUP. It's a great tool. So do VLOOKUP here and here. Oops. What is that? Okay. I hit some kind of button on my pen here. Okay, use VLOOKUP for these 2 rows. And then we can take the difference in energies. So this is just delta E. This is just, n prime minus n. So that's just the difference. And so then we can calculate that energy difference into wave numbers. So we just calculate it in wave numbers. So these top 6 or 7 rows should not be that controversial. The only trick would be the VLOOKUP. And so that's in the handout. Now we're talking about the Boltzmann factor row. So we have En minus E1. And so you can anchor this cell up here at E1. You can pick whichever one. You can go to that original page, or you can anchor that cell. And then you can just refer to this row here. So like if you're right here, just refer up to this one, this energy, and this energy. You take the difference between those two, divide by KT, put those constants on the front page, that control page. So you have Boltzmann's constant up there, and then you have the temperature. The degeneracies for all of these are 1. So you don't even have to put it in there. You're just multiplying by 1. And so you can just get rid of that whole degeneracy piece. And then we just did the TDM integrals. So use VLOOKUP for this one too. And so now we have the stick spectrum. So this one is this one times that one. So it's the Boltzmann factor times the TDM integral gives you the stick spectrum. And this is where you were saying you hit a snag. So we're going to plot first. We're going to plot the stick spectrum versus delta E, okay, and then we're going to plot the stick spectrum versus wavelength. So you can plot it versus either one of those, okay. So here's the stick spectrum versus delta E, okay. And you don't get this.
I get basically the exact thing, but I shifted out of negatives because I'm pretty sure I did something
Okay.
horribly
Okay.
wrong.
Okay. Interesting. Where could that? Where could a negative show up? I mean, if you had these two, like in calculating your delta E's, if you had these two switched, like if you did, you know, this row minus that row, then it would be negative. Okay. Okay. Yeah. Sure. So, but it's definitely probably something on this page. Yeah. If your other blocks match this lecture, then you should be good. Then it's on this page. Yeah. Did you do the minus 100% error bars and all that? Was that okay? That's a neat little trick. So to get these vertical lines, this is a minus error bar. So you have the data points here. A minus 100% error bar. So in your spectrum, you can add error bars. And that's one of the options. So you have your plot in Excel. Over here, there's a little, let's see, it's on the right side. There's a little plus sign. You click it, and you can add grid lines and all kinds of things, chart title and so on. One of those is error bars. I like to click the little arrow and go down to more options. Click more options, and then you get a little panel that allows you to edit the error bars. And you click the vertical error bars, and you edit and make them minus only. You can do plus minus error bars, you can just do minus only. And then you can come down here and say minus a certain number or whatever, but you could do percentage and just do minus 100%. So you just put 100% in those. You're saying minus error bar, 100%. So no matter where the point is, it just drops a line down to 0, and you get a stick spectrum. So that's a really nice thing. Now, I went in and selected my error bars and made them blue for the blue transitions and so on. You don't have to do that. You could leave them black or whatever. It's up to you. It's your chart. Okay. So that's a nice trick. And then the horizontal error bars, because it typically adds both of them. You click on it and just delete. Click and delete. And then you get rid of the horizontal error bars. So this is how you make a stick spectrum. If we plot that by wavelength, this is what we get. Now notice it's a little deceiving because we have all of these transitions down here with really, really small intensity. These seem insignificant. But when we put a line shape on these, they all add together and we get a significant intensity of absorption there. Even though all of those peaks are small, the thing is they're all there and they can all absorb light. And so they all play a role in absorbing and all their intensities add up. Since we're dealing with absorbance, the intensity is proportional to concentration. And so you could think of it as a really strong concentrated sample there. There's lots of possibilities for absorption. And so the intensity is really high. Okay, so let's talk about this line shape process. So we have 4 possibilities for line shape. So far we've talked about the Gaussian line shape. And this guy, Billow, he's a scientist. He did a great book, Excel for Chemists, okay? And I pulled these line shapes out of his book. He's taken the normal distribution and then used it, like converted it all and uses terms that we're familiar with, like wavelength. Instead of sigma and x, like a normal distribution for statistics, it's the same function, but it's using wavelength, okay? And so we have our spectral resolution here. that delta lambda. That's the width of our spectral resolution in our spectrometer. And then this is the horizontal axis. And these are our transitions. And so you can see the center wavelength here. So we're plotting every wavelength. This is across every wavelength. So when we're way over here at 400, the intensity of this Gaussian curve is 0 because we're so far from the center wavelength. But as we get closer, because we have a line width of, pretty wide, it looks like our full width at half maximum is 200 nanometers. So when we're right here, we're getting close enough to that transition that we start to see some absorption. And then here's our maximum. The peak height is this intensity or dipole moment integral. And so these are the three pieces that go into a Gaussian line shape, or any line shape. You have to have an intensity factor, you have to have a width factor, and then you have to have the center of that peak. Here's the Lorentzian line shape. I'm going to flash back and forth, look at the curves. Gaussian, Lorentzian, Gaussian, Lorentzian, Gaussian, Lorentzian. What do you see? What do you see in the Lorentzian curve? So I'm going to go back to Gaussian, Lorentzian. What can you describe about it?
Beginning absorbance, beginning and ending absorbance is higher.
Yeah, it's got a wider feet, like it sticks out further. Yeah, it's fatter at the base. Yeah. Now, why do we care about the Lorentzian? In super high resolution studies, this would be the peak shape you would get from the Heisenberg uncertainty principle. So this is the best you can do, is a Lorentzian line shape. So if you're dealing with gas phase spectra, single molecule in the upper atmosphere, there's no influence from other molecules, super high resolution laser, this is the line shape you would see. Like if you plotted that spectrum, they would all have Lorentzian shapes to them. Okay, if you had a really good spectrometer, that would be called the natural line width. Okay, or natural line shape. Who knows? Maybe you end up in a PhD program that does laser spectroscopy and you'll actually see a Lorentzian line shape. I did see partially one. So as you get close, you start to see a transition from Gaussian to Lorentzian. And so how do you model that one? It's not fully Gaussian, it's not fully Lorentzian. So what do? You don't just pick one, you actually do both. So it's a percentage, like 30% Gaussian, 70% Lorentzian. So that's the Voigt line shape. We're not going to use either Lorentzian or Voigt, but I'm just introducing it to you. Okay, you could, but this is going to be a real ugly equation because inside your Excel peaks, you'll have both the Gaussian thing times 1 minus b and the Lorentzian thing times b, and you'll add them all together, and that would be one nasty, ugly equation. But it could be done. It could be totally done very easily. And then the last one, this is, I guess it's, I can't decide if it's my favorite or not, but it is fun because this one is asymmetric. See, this peak tails. And so this is a really useful line shape. It's called the log normal line shape. It's a pretty ugly equation. Look at all that. You got logs everywhere. And we have this asymmetry parameter multiplied by delta lambda. And up there, asymmetry squared minus 1. And so this asymmetry parameter rho, that's the Greek character rho, has this difference. High, so from the wavelength high to the center divided by the center minus the wavelength low. So you see here, this line width is not centered on the center line. So you have a high wavelength, you have the center line, and you have the low wavelength. And so the asymmetry parameter is this piece divided by that piece. Okay. Now in this particular case, this asymmetry is less than 1. You see, this is a smaller piece, this is a bigger piece, and so it's going to be less than 1. But it could be greater than 1. So it could tail the other way. So if it tails the other way, the high might be over here, the center's here, so that's a big piece, and then this is a small piece, and so it tails to the right, then it's greater than 1. So the asymmetry can be greater than 1 and it tails to the high numbers, or it could be less than 1 and it tails to the low numbers. The only thing it can't be is 1. Because if it's 1, we're taking the log of 0 and it blows up. Okay? So if rho is 1, it's rho squared minus 1, which goes to 0. And then we're taking the natural log of 0, and the log of 0 is negative infinity. Is that right? Yeah. And then it blows up. So it can be 0.999, or it can be 1.001, but it can't be 1. So if you're trying to measure just a slightly tailed peak, I mean, if you have a perfectly symmetric peak, don't use this line shape, because this is for ones that are not symmetric. These are for ones that tail. Okay. All right. So that's why I say it can't be 1. All right. And that's another, I think that's another option in your extra work on the project, is you can model your spectrum with a log normal line shape and see what happens to the spectrum and play around with it. Change the asymmetry parameter, make them all tail to the right, and then you see it's a crazy spectrum. Make them all tail to the left. Maybe it's totally different. And you're not changing anything about the molecule. You're not changing the transitions. You're not changing the spectral line shape. You're just changing whether it tails right or left. And so that can have a huge effect. So here's our spectral convolution. This is how we put it all together to get a spectrum. So we now have our spectral line width. It helps go through the it helps to do this beginning and ending wavelength, and we can talk about that more, but I want to get to the meat of this one. And so here we have the height. The stick spectrum is the height. The wavelength transition is the center, okay? And our wavelength values over here. You see those right there. And then each peak has its own line shape peak. Like each transition has its own peak. So this is the 1 to 2 transition. And this one is going to be the 2 to 3 transition. So it has its own peak, Gaussian shape. Okay? And then the 3 to 4 transition has its own peak, and 4 to 5, etc. So every transition has its own peak. It's very simple. You type in the same function, copy it over, hit down, copy it down, and it's very easy to multiply this all the way across and do it 15 times or 36 times. And then when you get all of these done, you have the absorbance equals the sum of BIG, right? It's big. We want it big. So that's the sum. This total sum right here, A is equal to the sum of BIG. We have the Boltzmann, we have the integral, we have the Gaussian. So at that wavelength right there, this wavelength, we have that intensity summed all the way across. This is happening in your spectrometer. You have the light source, you have the monochromator that splits the light, and we pick a wavelength and we send it through the sample. And the light doesn't care whether it's a 1 to 2 transition or 2 to 3 transition. Any transition that's allowed at that wavelength, it can be absorbed. And the detector detects less light than it does in the blank. Okay. And then we pick another wavelength, so we move down a row, and then we sum all the transitions that are at that wavelength, and then we just scan one wavelength at a time and absorb all of the light that can be absorbed, and we get the total spectrum. So all signal contributions at each wavelength are summed together and plotted, and that's what we get. So now you know everything there is to know about a spectrum. Okay. So you can sit at any one of these wavelengths and scan to 300, and at 300, this transition, which is the 4 to 5 transition, and then the 3 to 4, and then the 2 to 3, all absorb right there, and that's the total intensity. Yeah. And all those insignificant transitions down here have become very significant. This region is the most strongly absorbing, but it has some of the weakest peaks. And that's what you're going to have. This guy, that's a beautiful plot. And the fun thing, and we're going to play with it on Wednesday, is now I'm going to pull the spreadsheet up that y'all are building on Wednesday, and we're going to play with it. We're going to change the mass and change the wavelength and all of that stuff. And so I'll have some fun on Wednesday. I hope you guys, when y'all are working on yours, you'll play around with it and do some of the things that I do. And so Wednesday's not really going to be a lecture. It's going to be just having fun with this spreadsheet and answering questions about it so that you guys can be successful. Okay? We got 1 minute. Anything that you want clarification while we're here? All our brains are engaged. Yeah, very good. Very good. All right.